we want to talk about about the flux integral. Now let's talk about flux for a minute. I don't have a real good picture of flux, but anyhow, the f dot t dr, which we often represent by an integral of pi plus qj dot dr, in 2 dimensions, because we're still with Green's theorem, we haven't gone into higher dimension yet. The f dot t dr integral, which is also written as f dot vector dr, this dr being magnitude of dr, this being the magnitude and direction of dr, the vector. And incidentally, your text, a lot of text will use ds here, and that's not bad either, but dr works just the same. Okay, so f dot dr, or this, is this integral, which by Green's theorem is this integral. In other words, this integral over the closed curve of pi plus qj dot dr, which is integral p dx plus q dy, because dr is dxi plus dyj along your parameterization. Now this integral is equal to the integral over the interior of the region of qx minus py with respect to area. Okay, that's the integral we have, and what that integral represents is if you have a closed curve with no holes and so forth, with a simply connected region, and you have a vector function in space, and that vector function looks like this around the boundary. What you're doing on every increment, and if you have an increment which I've indicated, let's say between these 2 points, so you've partitioned your parameter space, your parameter interval, and you've got this interval out here on the curve, and at a sample point in the curve you have this vector, then you simply take the component of this vector parallel to the curve, and that's the thing you're going to add to the sum that leads to the integral. In other words, then if you integrate the component of every vector parallel to the curve with respect to distance along the curve, you're going to get this line integral. And that's a tangential component. That's what we would use, for example, if this is a force field, to calculate the work done by the force field around this interval, around this curve, sorry. The flux integral, and maybe I should have, and I'm going to here, indicated perpendicular components. The component of each vector perpendicular. So this vector has a component parallel and a component perpendicular to the curve. So I'm going to go ahead and just kind of flesh this out a little bit. I'm going to draw the parallel components, approximate parallel components of these vectors. Again, the components parallel to the curve, and this one is pretty much parallel to the curve, isn't it? So is this one. But this one has very little parallel component, and more parallel component, and more here, and this, and this. Okay, so these are the components of the vectors parallel to the curve. Again, those components, if this is a force field, would indicate the work. If it's a fluid flow field, it indicates circulation. And of course, we've talked about the circulation interpretation. Okay, now, if we do the perpendicular components, not much perpendicular component on these vectors. But this one's mostly perpendicular. A little bit of perpendicular here, a little bit more here, somewhat here, and not much here. the perpendicular component, if you think of a fluid field right now, would be the fluid escaping this region. And you see that at every point where I've indicated a vector, fluid appears to be escaping the region. The velocity vector, fluid velocity vector, is always out of the region, or at best more or less parallel to the region. Doesn't mean there couldn't be some that go into the region, but that's not the case with this picture. Okay, well, you take the total of all these vectors, and that's the amount of flow out of the region. So if you have your increment delta r here, so I put a little circle around this and an arrow down here to indicate this is an enlarged picture of this. Here's your f of x star y star, or xi star yi star if you have everything partitioned. And here is the component of that force parallel to the field. And here's the component perpendicular to the field. Component parallel adds to your circulation. The component perpendicular adds to the flux. Okay, so I just indicated here that f dot delta r vector is the same as f dot t times delta r magnitude. T being the tangent vector, being the vector in the direction along the curve. Okay. Now the flux through the increment is then f dot n delta r, where n is the outward unit normal. Okay, so I don't have the outward unit normal, but it should be clear that if this is your delta r, then with the curve in this orientation, your outward unit normal is in this direction. And that leads to the idea that total flux is the integral of f dot n dr. Now, again, if f is pi plus qj, then the f dot t delta r integral is this, which is equal then to the integral over the two-dimensional region of the qx minus py, and we're familiar with that. So here again is your delta r. Here's your pi plus qj. If delta r is delta xi plus delta yj, then pi dot qj delta r is just p dx plus q dy, which is justification for this step. Already mentioned that. Now, observe that the vector negative qi plus pj is perpendicular to the vector pi plus qj. Okay, so if you want the normal component of f, it's going to be this. It's going to be the negative qi plus pj. And my sentence doesn't make sense. So the contribution of the normal component would be this dotted with your delta r. And that would be negative q dx plus p dy. So let me fix my sentence. I'm not going to get a good sentence out of this no matter what I do. I'm going to take the is out of consideration here. So the normal component of f implies that you want to calculate this dot product, which is q delta x plus p delta y, negative q delta x plus p delta y. Again, because this is perpendicular to this. and of the same magnitude. Okay, so our integral of pi plus qj dot n is what I've done here. Here's your normal component times your delta r. Okay, that sentence is messing things up, but this is the normal component. Well, this is the integral of the normal component, and that integral then has to be equal to the negative qi plus pj dot t dr, which is this, which is your negative q delta x plus p delta y, which is the integral of px minus the negative of qy dA, which is just px plus qy. That x almost looks like I tried to change it to a y, but it's clearly an x. Okay, clearly needs to be an x. So there's the integral. And really all we've done here is we switched the roles of p and q and made the q negative, so that instead of getting, as you would get, well, I don't want to make those parallels. Just by switching the p and the q and making the q negative, then you know from Green's theorem that it's going to be the x component of the j, going to be the x derivative of the j component minus the the y derivative of the I component. Okay, so what you have here, negative y derivative of the I component and x derivative of the j component. So x derivative of the j component for the normal vector is this, and the x derivative of the I component is the x derivative of the y derivative of the I component is the y derivative of negative q. And you have a minus here, just like you do over here for all the reasons that we developed when we did the integral over the simple little rectangle. Okay, so we end up with this. You want to think about that. It's just a matter of signs and what takes the place of what. So p has been replaced by negative q, q has been replaced by p because we're doing the normal component now, and that gives you this. The rest is quite simple. So in summary, the integral of f dot t dr is the integral of pi plus qj dot dr, which is the integral of p dx plus q dy, which is qx minus py dA. We already know this from Green's theorem. And the flux integral of pi plus qj dot n is the integral of negative q dx plus p dy, which by Green's theorem is the integral of px plus qy. And you want to try to remember the reasons why that change is made and what everything means.